Arginine is one of the 20 amino acids that's used to make a protein within the human body. Just like every other amino acid, there's the center carbon, the chiral carbon, the stereocenter carbon, the carbon that has 4 different things attached to it. One of those things that's going to be attached is this carboxylic acid, where you've got a carbon with 2 oxygens. One of those oxygens is attached to a hydrogen. You've also got an amino group where you've got a nitrogen with 3 hydrogens attached to it that's connected to the carbon. This nitrogen should only have 3 total attachments in order for it to be neutrally charged. So the fact that it has an extra hydrogen attached means it's going to carry a +1 charge. Then this carbon also is going to have just a straight hydrogen attached to it. And then the thing that makes it individual, unique, its own amino acid is the R group that's attached to it. At the lowest pH possible, arginine is going to be fully protonated, aka everywhere you can have an extra hydrogen, there's going to be an extra hydrogen. As the pH goes up, there's going to be hydrogen loss from this molecule that has to go into the environment to balance out the loss of hydrogens from the environment. The first hydrogen that's going to be lost from arginine is going to come from this carboxylic acid, and that's going to happen at a pH of about 1.8. This oxygen is going to gain back its lone pair, and so now this oxygen is going to carry a -1 charge. Blue is still going to carry its own +1 charge, and this R group, this nitrogen, also has 4 attachments and it should only have 3. So this nitrogen is also going to carry a +1 charge here. So you've got a +1, a +2, and a -1. So overall, this molecule is going to carry a +1 charge after a pH of about 1.8. Now, if you keep going up, keep going up, keep going up, the second hydrogen that's going to be lost is going to come from this amino group that's directly attached to this carbon. And that nitrogen is going to gain back its lone pair, and now it's going to have a 0 charge. It's going to be neutral. So now we're going to have a -1 charge here. We're going to have this neutral charge here, and we're still going to have this +1 down here. So above a pH of about 9.0, this is going to be the form that predominates. And then you keep going up in pH, keep going up in pH. When you finally get to a pH of about 13.8, the hydrogen from this R group, the very bottom nitrogen down here, it's finally going to lose its hydrogen and gain back its lone pair of electrons. So now this is going to have a charge of 0. This is going to have a charge of 0, and this is going to have a charge of -1. So above a pH of about 13.8, this molecule is going to carry a charge of -1. At physiologic pH, or about pH of 7.4, what the pH is like in the human body, this nitrogen is still going to have its extra hydrogen, so this is going to carry a +1. This is going to carry a -1, so this balances out to 0, but this is still going to carry its extra +1. So overall, at physiologic pH, arginine is going to have a charge of +1. Now let's talk about its R group. All of these things in blue are nitrogen, and you can see compared to almost every other amino acid, there's a whole lot more nitrogen here. All of these bonds with this nitrogen are going to be some kind of a polar bond, and so you've got some polar bonds going on here, but you've also, more importantly, got an extra hydrogen attached down here, which is going to carry a formal charge. So you've got partial charges from these polar bonds, and then you've got an actual formal charge. Formal charge takes precedence. So this is considered a basic, because this is positive, a basic amino acid. Because so many bonds between this carbon, all of these can move around. These are all connected to some kind of a nitrogen. This is called stabilization or resonance stabilization. This double bond can move over here, and then this hydrogen can move somewhere, or it can just have a lone pair. Things can move around in these bonds, and that allows for it to take even more energy to remove one of these. And that's why this has such a high pH before any of these hydrogens are lost, because of this stabilization of this resonance with these extra nitrogens to this carbon. Arginine is not an essential amino acid. You don't need to eat it for it to show up in proteins in the human body. You can use other molecules to make arginine, and a lot of this happens within the small intestine and the kidneys. However, if you don't have full function of your small intestine or your kidneys, aka your body's not able to synthesize arginine, then arginine becomes an essential amino acid. You've got to eat it. So either your small intestine and your kidneys work, or you have to eat arginine in order to be able to see arginine show up in your proteins.